So the topic for this discussion is about one of the applications of DE, which is geometric application. So for the geometric application, you just have to remember some points. Okay, so one of it is if we have a graph of a function. Let's say this is a graph of the function y is equal to f of x. So that at a certain point, every point in the graph of the function has a tangent line. Okay? And the slope of this tangent line is simply dy over dx. If you could still also remember in the or during your differential calculus that the slope of a tangent line at a certain point xy, okay, is dy over dx. Okay. And then another thing, if we have a tangent line, we also have what we call a normal line at the point. So this normal line is perpendicular to the tangent line, and the slope of the normal line is just a negative reciprocal of the slope of the tangent line. Okay, and that will be equal to negative dx over dy. Okay, so these are one of the things that we have to remember before we will proceed to our examples of geometric applications. Okay, so this is our first example. We are to find the equation of the curve passing through the point 3 and negative 2 and having a slope at any point xy equal to x squared plus y squared over y cubed minus 2xy. So when you say slope at a certain point, that means the slope of the tangent line at that point of the curve. So if slope at any point xy is expressed as x squared plus y squared over y cubed minus 2xy, okay, then this is also equal to dy over dx since the slope at a point in the curve is simply equal to dy over dx, or first derivative of y with respect to x. So from here, we already have a differential equation to which we just have to get its solution, and that solution will be the equation of the curve being described in the problem. Okay, so this is obviously this is a first order equation or first order DE. Okay, so let's try to separate. Okay, so we have dx, then we have equals y cubed minus 2xy dy. Okay, so let's try to convert it to the general equation of DE. We have mdx plus ndy equals 0. So we have x squared plus y squared dx. Okay, then we have plus 2xy minus y cubed dy. Okay, so as you can see, m and n here are both could not be factored into functions of x and function of y, so this is not variable separable. Another thing, this is also not homogeneous because this is of second degree, but one of the terms is in the third degree. So this is not homogeneous. Let's try if this is an exact DE. So we have partial m with respect to y. So this is our m, x squared plus y squared. That will be 2y, and then for n, this will be our n, 2xy minus y cubed. Partial with respect to x, partial derivative. So y will be constant. Okay, and then so we are going to make y as a constant. So therefore, derivative with respect to x will be 2y. Okay, so therefore this is an exact DE. So we could easily get the solution. So for an exact DE, what we do is get F1. So that is integral of mdx plus f of y. So we have integral of m, which is x squared plus y squared, partial of x, partial differential x, okay, plus f of y. So that will be, we'll make y squared as constant. So we have x cubed over 3 plus xy squared. Then we have plus f of y. And then for we have f sub 2, we have integral of n partial y, then plus g of x. We have integral of 2xy minus y cubed. Then you have partial differential y plus g of x. So this is, you have xy squared, okay, then you have negative y raised to 4 over 4, that is plus g of x. Okay, we will continue at the other side. Okay, so therefore the solution, general solution, will be, you have the common xy squared, then you have plus x cubed over 3, okay, then minus y raised to 4 over 4 as f of y. So this is the f of y, this is the g of x, this is equal to c. So this is yet the general equation. Now we could actually get the particular solution because it is said here that one of the points of the function is 3 and negative 2. Okay, so this means that if it passes the coordinates 3 and negative 2, then therefore at 3, negative 2, okay, where this means that at x equal to 3, y is equal to negative 2. So we could get c in this equation, okay, so therefore we have x is 3, y is negative 2 squared plus 3 cubed over 3 minus, so we just substitute here, negative 2 raised to 4 over 4 equals c. So c here will be equal to, let's see, that's, I want you to be the one to calculate, but I guess this is 17. So we now have the particular solution, which is xy squared plus x cubed over 3 minus y raised to 4 over 4 equals 17. So this is already an acceptable equation. And it's up to you how will you simplify this. Okay. So this is now what is being asked in the problem, the equation of the curve that passes through 3 and negative 2, and the slope at any point is described as x squared plus y squared over y cubed minus 2xy. So this is the equation of that curve being described here. Okay? Right, next we have find the equation of the curve such that the x-intercept of the tangent line at any point xy on it divided by the square of the ordinate is a constant. So when you say ordinate, if we have a certain point xy, so this is the abscissa and this is the ordinate, okay? If you could still remember, this is what you call the abscissa. So the y coordinate is what you call the ordinate, okay?